Welcome to my presentation with the title Wiring Harness Process, Holistic, Consistent, Model-Based and Intelligent. This is the agenda for today. Smart Cable has been developing tools for physical wiring harness production process for 20 years. Our tool chain is model and knowledge based and it works across various domains. The 3D topology, wiring and configuration come together in our data model in such a way that 3D views, physical wiring harness, and 2D views, documentation, wiring harness drawing, and design board can easily be derived from a model. We competed with tool-oriented processes. In part 1 of my presentation I will explain the essential differences in the methods, and in part 2 I will present the model-based procedure by showing examples from the daily work of a wiring harness designer or layouter, and in part 3 I will offer a glimpse to the near future. The wiring harness process is complex and will grow even more complex with new requirements. In today's processes, different tools are used in various design phases. The tools communicate with one another via interfaces. The concept: use the best in class tool for each task. It sounds appealing, however, it endangers the efficiency of the total processes and implies the risk that the engineers are thinking only locally. Changes are often made directly in the drawings due to time pressure. The synchronization of versions is missing. They have to be reported back to the respective sources. There is generally no direct link between the tools for design and for manufacturing, so the manufacturing documentation has to be updated separately. I think you are probably familiar with these processes. In our model-based process there are several significant differences, but here the tools communicate directly via the data model. An external interface is required only to import wiring information. When OEMs use CATIA, the 3D topology is taken directly from the CATIA model. By NX we all use also an interface. The physical wiring harness is the goal of a wiring harness development. Thus, compiling manufacturing documentation is integrated into the process. Changes to the initial wiring data are very common throughout the entire life cycle of a wiring harness. Any change to the wiring can have an impact to 3D topology, so changes have to be validated across all domains. The change management considers a change to be delta information on the data model. The change management unlocks significant potential for rationalization. I will demonstrate this in the second part of my presentation. Smart Cable has added a knowledge base and a supervisor to its tool chain. The knowledge base can be continuously updated to new findings, experiences and specifications. Engineering knowledge is structured in the knowledge base in such a way that algorithms can read the knowledge and use it as a basis of decision making. The knowledge base is managed by the supervisor. This knowledge base is used for compliance with design rules and for generative design. For example, if I have a splice in that area, we must create a waterproof grommet for it. And last but not least, we add a new member to our tool chain for design and rating harness architecture. With name is HiTool. The criteria catalog serves as the basis for assessment. We use an engineering knowledge base for the assessments. This tool is still in the development phase, missing links including interfaces to the wiring design and to the 3D topology. Now we come to part 2 of my presentation. On 4 examples from the daily work, I will explain the advantage of our approach. The smart cable data model ensures the data consistency, design rule conformity can be evaluated, and for this I can select the best view. The integrated change management transforms and distributes the changes to impacted objects. The changes are validated and documented. This guarantees data quality and transparency. Particular importance is placed on verification and validation throughout the entire toolchain. Verification applies the design rule catalog applicable to the project. Catalogs can be extended as needed. Including simulation in the process enable the dynamic behavior to be validated. Cost transparency is ensured even for changes without any manual effort. Optimization through the application of comparative evaluation is important in every phase. Now we come to my first example. Here I will show you to fulfill OEM specifications, in this example the maximum spacing of fixing. The result of with checks or validation is if the model is correct or if it's not correct, and if it's not correct, the program shows you the error location where is the situation. For this one I have prepared a short video. I search, for example, in fixing, here in my 2D drawing, my 2D view of a model. Here I have all the information from the fixing, the part number and so on. I see the location in the 2D drawing. So from here I can switch the view, I can show me the same fixing in the 3D environment. Here I see it, where it's located, and here I can run the check to test all the distances from fixing. I have I define the maximum allowed length for fixing to fixing and connector to fixing. I run the simulation. After the simulation I get a list with errors, and if I click on a line I see the location in my 2D drawing where from the element that not respects that rule. In example 2 I will show you our automated change process, the synchronization of different versions and the documentation of the changes. The task here is you have a change and you have to introduce the changes from one model to the other model. We can have changes in the sources of 3D topology or in the source from the wiring, and the video will show you how to introduce the changes from 3D or wiring into my 2D drawing. The result is a synchronized and documented new version. Here I have the version of the 2D drawing, and I have some changes in the corresponding 3D version, in the new 3D version. So I switch back to my drawing. I start my comparison. I select the mode updates from new 3D. I select the newest version of my 3D model. The comparison gives me 9 modifications, 9 differences between the models. And here I see the data list from the 2 versions. I have some elements that are added, some elements updated or deleted. Some of the operations are interactive. So the program and the user, the programs help the user to introduce that differences in a drawing. Here the user only must select the endpoint of a new branch, and all the other operations can be done automatically. I have updated in segment length and wire protection to connect the connectors on the ends to the segments, and to move one fixing on a segment to a new position. So if my list is empty, now I have no changes more between the versions. I can close that one here, finished it. And now I do the same with a new version of wiring. I select the KBL with the wiring information. I got 22 modifications, differences between the models. Here I have a list of the differences, and in this case I can do all, I can update my model with all the differences in one step. On the end, the model will be validated and I get a summary of the changes. From here I can create my change report. I have some global information about the change. I have a data list for the wires. Some wires are added or updated, especially the wire lengths. I have a data list from the BOM. And also I have some screenshots with the elements where I added, color it in green, or with the changes, color it in blue. So now we come to my third example, which will demonstrate you the cross-disciplinary verification and validation interdisciplinary to guarantee data quality and consistency. You have 2 different tasks. One is the verification, use a rule catalog to check the wiring harness model, or the validation to simulate and display dynamic behaviors on an architecture as reaction on an injected error. The result is you have the design rule consistency and the response to injected errors are shown. Here we have an example from the architecture design from our new tool HiTool. In the video you see an architecture design with some actors and sources, and you see here the redundancy. You have the actor has 2 ways to the sources, 2 different ways, so redundancy is given on a static view. To see the reaction, the validation on a dynamic way, we start the simulation. In this case we will inspect the reaction by error injection from a short circuit. I initialize my model, so all the components are okay and ready. I define my parameter set for the simulation. The simulation tool is Simulink and the duration is 10 seconds. I inject my error in a short circuit in the secondary subnet after 4 seconds. To run the simulation, at first we have a digital transformation from the model, from the architecture design to the simulation model. the simulation is runs, and we transfer back the results from the simulation, and we can visualize it here. You see after 4 seconds, you see here the voltage and the currency, and after 4 seconds you see the peak from the short circuit. This is for the secondary net, and after it the secondary net is isolated, so every actors must use the primary net. You see also here the peak, and you see that the currency is duplicated after that 4 seconds. And on the end we also can have here a check with a catalog, and we will see, we run the check, and also we will see that we have here one rule that is not respect. Here the maximum currency, our currency is out of range for that DC-DC bundle. In my last example, I will show you Reoptimization throughout comparison of alternatives, in which case the comparison of production costs at different locations with different resources. The result is the transparency in costs and resources. To do that one, I specify a configuration on my model. The material costs are calculated from a configured BOM. For the manufacturing time, we will run a work planning simulation based on a standard time catalog, which is valid for the specified plant with specified resources, and also we calculate the degree of automation. I will run the video. Here we have the configured model. At first I select the specification and resources and time catalog from my plant 1. I run the work planning simulation and calculation of material costs. I will show you the result of the work planning simulation. Here you see for each element the manufacturing instructions, working steps with the times it's needed for each element from the configuration, and on the end you have a total time to produce that configuration. For plant 2 we have a special automate. We can define the parameters of that automate, and at first we calculate the pre-assembly of the elements of objects, what we can handle on that automate. The algorithm calculates automatic the subset or the pre-assembly of that one that fulfill the requirements from that automate. I have a report of the wires, what I can handle on that automate. Here you see all the wires which can handle an automate, and I have a second report with the wires where it's not possible to handle on that automate because the length is not matching requirements or the cross section is not matching the requirements from that automate. So now I select my parameter for the second plant with the new resources and the new time catalog. I run the work planning simulation, and I see in my output of the work planning simulation that a lot of the wires now have can handle automatically on that automate, and on the end I have a new time to put that pre-assembly to the board, and also I see that the manufacturing time is reduced. And now I come to the end of my presentation. Different engineering domains come together in the wiring harness process. Networking between wiring, 3D geometry and configuration has to be ensured. Driver assistance systems require interaction between the domains and dynamic analysis. E-mobility requires simulation, autonomous driving requires error-tolerant energy wiring harnesses. Checking that everything is correct can be successful only in a model-based process. Every change has to be verified and validated, a prerequisite being a data model that allows this. Access to the customer's expandable engineering knowledge base is also essential. Cost pressure can only be countered with cost transparency, time pressure with automation. Of course, this applies also and especially to the change process. Replacement of phase-oriented tools are necessary as phase-oriented tools cannot network. I hope that by showing this example I was able to give you an impression of the implementation in our tool chain. One OEM and several suppliers have been productively using V5H for years. We continue to develop and adapt the product to meet the needs of tomorrow. So, thank you for your attention.